You do need to put your section on your quizzes and exams, etc. Okay. How do we do on the first one? Hopefully pretty straightforward. So the SN1, because we have a tertiary site available. So we ionize, make cation, and then chlorine attacks. I didn't show mechanism, but any questions? Good old Williamson ether synthesis. Sodium makes the alkoxide, generating hydrogen. The alkoxide attacks the carbon, kicks off the leading group. And so, under my hand used to be a chlorine, now it's the nucleophile. At this carbon where the backside attack took place, we have inversion. No change over here.
You changed it.
You just flipped it.
No, you just flipped it over.
No change. It's R there, and it's R over there. Just like this. Did I change the hand to the other one? No. No. Still the right hand. Thumb can be on the left, thumb can be on the right. It's still the right hand. Right? You draw it many ways. How we do? How we do, Nancy? Magnesium with diethyl ether is going to make Grignard here, but we know it reacts as if it's carbanion. Okay, so it's like ionic, ionic. So it gives us a carbanion nucleophile. That can add to oxide on the right. Let's seriously hindered. Open it up, and we're going to get product shown. We make this bond here. Oxygen comes up minus. It picks up an H from water. Here we get it's inversion. That's what we were doing with this, right? There's no change over here, although I realize that it's not chiral anyway, so you really don't have to even worry about it. It's two methyls, but there wouldn't be any change over there. Any questions about that? It's a standard reaction. Grignard reagent reacting with oxide, opening it up. Sadia, that's good? Mechanism. Give you something with a variety of steps in there. First thing I did, protonate the epoxide, yay. Under acidic conditions, usually the first thing we'll do in a mechanism is protonate something. At that point, what am I trying to do here? Take a quick look. I got this nucleophile on this end carbon here, methanol. Methanol is a weak nucleophile. Okay? Question?
I didn't show proton transfer. I showed H2SO4 with obtaining that hydrogen and then later adding it.
So you showed two proton transfers?
Yeah.
That's okay. We'll talk about proton transfer. Ionization would give this cation. Tertiary cation. It's going to be very favorable. Methanol can now attack. Basically, methanol is weak, so it's going to do SN1. Okay? Do SN1, we're going to do tertiary cation. Methanol attacks, we get this, we got to lose the H. Okay, at this point, H plus transfer. We'll do lots of this. Now you can take by HSO4 minus and take the H and show that neutral plus reforming H2SO4. But at that point, you can then come over here and have the alcohol take the H back from H2SO4. Or you can sort of omit that step. You can also use water to take the proton, right?
Yeah.
Some of you do that? Well, this OH is just as basic as water. So why not essentially have this OH take the proton? And that's essentially what I've done, except it may not be internal. It may be one molecule OH taking the H of another molecule. We will do proton transfers a lot going forward. Basically, when you have a lot of acid, okay, pretend I'm acid right here, and all of you are OH groups. Which one of you is going to get the acid? Well, it's going to bounce around like a hot potato. I mean, you're protonated. Well, why come he can't be protonated? Well, he can take the H and leave you with a lone pair. Well, why come she can't be protonated? Well, she can take the H and leave you with a lone pair. That H is bouncing all around when you have equally basic atoms.
This is like a really small. In the mechanism, does the carbocation technically go next to the phenol and then the other hydrogen comes over?
Phenol. Phenol is an OH. Let's finish it up here.
I'm not contact.
Water can ionize. What do we need to get here? We need to get in, basically from here a double bond, so this is sort of elimination chemistry. Ionize, you can't do anything else. Here, but we need to put the double bond in there, so what do we need? Hydride shift, now we can put the double bond in. You could actually maybe do another hydride shift. And I would really only ask you to all just do one. But from here you can get the product by something taking the H, moving this in. This is the fast stuff of an E1. You can use that to reform H2SO4. You can use water to take it. So a variety of steps. It's all classical chemistry. How do we do?
Good.
Okay. Okay, it's supposed to be a doublet 6H, multiplet 1H, doublet 6H, yeah? Okay, can you have a CH6? No. So it's most likely what? Yeah, two CH3s are equivalent. How can we make them equivalent? Maybe bonded to something like this. These are equivalent. How do you make this a doublet?
Add one H.
Have an H here. Okay. Multiplet 1H. Well, what would this be? That's multiplet 1H right there. So there's half of your what you need. Now you need a multiplet 2H. Well, actually, if you just draw CH2 over here, let's see, we have doublet 6H. This is what? Multiplet 1H? What would this be at this point if nothing else is there? It'd be a doublet 2H, but it doesn't say that. It says multiplet 2H. How do we want to make this a multiplet? We need more splitting. If we put another CH2, now what is this? Multiplet 2H. And the last thing we need is triplet 2H.
Oh, that's CH2 again.
So what would this be?
Triplet
Triplet 2H. But you can't just have that unless you want to be like, hey, it's a carbocation. There's got to be something else here. What else could be here? Maybe a chlorine. Not an H. Okay, well, does everybody get that right there?
Yeah, why is that's
What would this be? Triplet, which was the last one. Why is the white question, guys? Why is this not a quartet?
It's 2 times 3.
complex splitting?
Because these H's aren't equivalent. You're saying there's 2 on this side and 1 over here. 3 plus 1 is 4. You only do n plus 1 when the H's are equivalent. Are these H's the same? No. You have to do it n plus 1 twice. N plus 1 twice. This makes it a doublet. And then this splits triplet, so each one of these becomes 3. And you actually get 6 lines. Beyond 4, we call it a multi. It's complex splitting. We actually have it covered at the page, but I told you how to do it. Complex splitting. Question?
If you were to replace that last CH2 and CL with a amine, would that still work?
With what?
An amine?
Like NH2?
Yes. Would that still work?
No, we haven't talked about that, but you often don't get splitting between C and N.
Okay.
This would be a singlet, and this will probably be a doublet, because it doesn't get split by that. And also, I don't know how you get a triplet. Oh, I see, because you're saying this is going to be a triplet?
Yeah.
Okay.
Is that exactly?
If you see splitting, it might work. A lot of times you don't see the splitting with this here. It could be other things. Somebody said oxygen, but it can't be an OH, because if it was an OH, you would expect the peak for the H. But it could be an ether. I bet you I do lots of products. It could be an ether. And you can draw the same thing on the other side. Because I did say relative integration.
But wouldn't that give you more?
More peaks?
For the doublet 6H, wouldn't that be like doublet 12H?
Yes, it'd be doublet 12H. And this would be multiplet 2H. It would be the same thing listed here, except that would be 12, 2, 4, and 4. Same relative integration.
Oh, okay, you're saying, all right.
Okay? Because this is really ratios. It's relative. I mean, this could be 60, 10, 20, and 20.
And it's still the same thing?
Same ratio.
Okay.
You also do this. This also fits where out here it's open in chlorine, I put a carbon, but I didn't have any H's on it. So basically you just end it with that right there, and there's no signals, or there's no H's. There's a variety here. How do we do on that? Did anybody get it? Good. Good. Anybody else? What was the issue with getting it?
Mechanism took a long time to write out.
Warren?
Just the mechanism. I didn't give myself enough time.
Okay. Mechanism need to be, just go. See steps, go. There's mechanisms in the workbook. Okay, this will be posted on the 3rd floor in the glass case as you walk down towards the lab. Let's look at NMR a little bit. Let's look at one more of these. It's this figure 14.23 here. 14.23.
Is that in the
NMR packet. It's where we left off at. We did 2 of these HNMRs.
I had a question. On the next page, you have a C5H12O at the top. Is that for the next one? I just didn't know where that was coming from.
Oh, yeah.
Yeah, I mean that is that's the formula for this one over here.
Okay.
Yeah.
Okay. Yeah.
Okay. Yeah.
With that one, Dr. Peter?
What?
With that one, there wasn't a significant peak for an O in the IR. Is it? Unless I'm blind.
Which one? The one we're doing? Okay, let's look at 14.23. Question?
Yeah, for the food lab for tomorrow, it requires that taking the products of an oxidation of alcohol.
I didn't hear you.
The pre-lab for tomorrow's lab is requires like predicting the product, but it's an oxidation of alcohols, and we haven't done that yet. So is that something that we do?
Okay, let's not look at NMR. Let's look at.
But also, there's a thing in the lab that has to cover carbon in it.
you haven't done that yet.
Well, no, I expect you to do that on your own. Let's do look at oxidation of alcohol. Basically, I wanted to try to get us more in tomorrow, because you can't just sit on it and then, last week, hey, let's do it tomorrow. You got to be working problems. I know a number of you have been asking questions. I'm not sure that all of you are really working in tomorrow. Okay? If you have questions about it tomorrow, please ask. There's plenty of problems in your textbooks, there's problems in the workbook, et cetera, et cetera. Okay, oxidation of alcohols. We introduced this. Primary alcohols oxidize the aldehydes and on the carboxylic acid. Secondary alcohols oxidize the ketones. Tertiary alcohols cannot be oxidized in this class. Okay? Of course, just about everything we say you can't do, you actually can do but it's just very advanced chemistry. Okay? Can't oxidize tertiary alcohol. This is what kind of an outline here. We'll go back and forth between this and the white, or the one you printed out yourself. So let's look at oxidation. First off, what reagents do this? We have the big three that I call. Okay? These are sort of metal oxidants. KMnO4, chromium trioxide, sodium dichromate, or potassium dichromate. These are all metals that have lots of oxygen on them. They act as oxidizing agents. Typically, you take these and your reaction's done under acidic conditions. That can be sulfuric acid or maybe acetic acid. Now with the bottom two, when you put them in aqueous acid, they both form chromic acid. So they both essentially form the same oxidant, chromic acid. Chromic acid, the chromium is chromium 6. You'll be able to do that from Gen Chem. Now if you add an alcohol to chromic acid, they will react. The alcohol will get oxidized to a carbonyl compound, if it's primary or secondary, but not tertiary, right?
Yeah.
Well, if the alcohol gets oxidized, what happens to the other species? It gets reduced. The chromium gets reduced from chromium 6 to chromium 3. Actually, it's chromium 4. It's really a 2-electron process. But chromium 4 is not stable, and it quickly goes down to chromium 3. So there's your redox for chromium. I'm not going to show anything with KMnO4, but of course the manganese would get reduced. So this is important. We're also going to have a chemical test because chromium 6 is orange, where chromium 3 tends to be blue. And so you can have a visual confirmation that the reaction is taking place. And that's actually going to be called a Jones oxidation test. Okay? Primary and secondary alcohols give a positive Jones oxidation test. That is, they'll turn your chromic acid blue. Will a tertiary alcohol do that? No. You see, you can say the chromium oxidizes the alcohol, but if you want to, you can say the alcohol reduces the chromium. It goes either way. So that's the Jones oxidation test. Tertiary alcohols give a negative because they're not oxidizable here. Nothing happens with them. Now, aldehydes also give a positive Jones. We'll have to talk about that. And by the way, does a negative Jones mean your compound is a tertiary alcohol? No, there's many other things that give a negative Jones. I mean, just a regular alkane gives a negative Jones. A regular ether gives a negative Jones. So don't get into blinders and say, hey, it must be a tertiary alcohol. Do what? If you know you're dealing with an alcohol, then you can say, hey, it must be tertiary. Right. Okay. So if we're going to kind of go back and forth here between sort of written stuff and stuff that's sort of typed out here. By the way, breath analysis, you know when you do a breath analysis on the side of the road, right? No? What do? They ask you to blow into it. They want to see how much orange you turn to blue. Because ethanol is a primary alcohol. If you blow in there and you turn a lot of the orange to blue, guess what? You'll get a free ride downtown. Okay, don't do that. But that's called a colorimetric analysis or something. There's some type of light analysis, and they can maybe like UV, because orange light is going to have a different UV absorbance than blue light. Okay, so that's just an application of where they're doing that at. Predict products here. Here we go. Classical, what we just did. We got a secondary alcohol. Here we have one of the big three under acidic conditions. Okay. By the way, we didn't do mechanism over there. I might show you a mechanism because it's something we can reasonably look at. But in terms of predict the product, well, go ahead. What's the product here? Do them both here. So down here we have a primary alcohol, one of the big three. And I'll just sort of show you the answer to the first couple. But what's this going to become? Double bond to oxygen, and it's a ketone. What did we lose in formula going to there? What nitrogen or two? We lost two H's. We also lost the H from the carbon. Okay, minus 2H. Very simplistic. That doesn't mean we produced hydrogen gas. Where did the H's end up? Well, we didn't do the mechanism over there. Okay? How about down here? What do you get? Well, if you lose two H's, you first get double bond to O. How many H's are on this carbon? Only one now. I like to draw in the H of my aldehydes. But what happens to aldehydes? What do we say up there? The aldehyde is not isolated, but instead it gets further oxidized to what? Basically, there's it, and this just becomes OH. You have carboxylic acid. If you're using one of the big three, it will not stop at the aldehyde. It will keep on. This is a further oxidation. You do need water here. That's where the other oxygen comes from. But do we have water in the reaction?
Yes.
Yeah. Aqueous acid. Okay. Let me give you an idea of how this takes place. And during test 4, we will learn that with water, aldehydes form what's called a hydrate. If you add water to something, we call it a hydrate. Okay? For water adds to the carbonyl. We'll do this during test 4. It's very simple, just adding the carbonyl. At this point, well, this is not isolated. Actually, this is an equilibrium back and forth. Now, if you remove two H's, what do you get? Hold on, I've removed the wrong 2 to get, it really doesn't matter. Okay, if we remove, just to make it clear up here, we remove, well, I'm going to have to remove this one and this one. That way the double bond will be here. We essentially do the oxidation of this. You put in the double bond, but guess what? There's an OH there. Okay? So it is another oxidation, but it also you have to have water. In the end, when you use the big three, it doesn't stop at the aldehyde, it goes all the way to the carboxylic acid. Ketones does stop there because there's no H, there's not another H to remove. Okay? By the way, I think it would be good to give you a little idea of the mechanism here. It'll be an abbreviated mechanism, just to give you an idea so it's not so much magic here. Let's take a primary alcohol. This reacts with the metal, okay? I'm not showing the metal form. It reacts with the metal to give, well, let's keep up with electrons. And let's do this. Let's just say metal plus, okay? Very generic. It might be 6 plus. This can react to the metal somehow, okay? What would that give? Give this one lone pair left. Plus charge. Okay? By the way, let's keep up with that lone pair that I just circled. Those 2 electrons. Somehow the metal gets on the oxygen. At this point, what are we trying to make? We're trying to make double bond to oxygen. Well, at this point, you can do a good old classical, now this is going to look a little bit odd because we don't do this making alkenes, but what if water took this H, these electrons moved in, and kicked the metal off? First off, what type of mechanism does that look like?
E2.
Looks like an E2. But the big problem is I'm using water, which is not a strong base.
Right.
That's because we're not making an alkene. Okay? A lot of the stuff we had limitations on from those reactions don't apply to other chemistry. Like, you never do SN2 on a tertiary carbon? Well, guess what? You can do SN2 on a tertiary silicon, which is just below carbon. Okay? So yes, this is an E2, and it should look funny to you, but we're making a much stronger bond here, and it's doable. Everybody agree that this arrow movement gives that, except, hold on, there's an H here, right? And that's still plus. And here's the metal. But what is now on the metal? What does this arrow mean to you? What is now on the metal? A what?
Electron, negative.
Well, a lone pair. So look at the lone pair. It used to be on the oxygen, but now it's on the metal. So the oxygen has lost electrons, or we can say the metal has gained electrons. You see the redox? We keep track of that lone pair. Okay. Now, where does this H come from? Well, there had to be a minus with this metal. Okay? Whatever that minus is can take the H, etc. I'm not giving you a full mechanism. Okay? Just trying to give you an idea. Now, there's other things that can get on the oxygen to do this. Maybe a halogen can get on the oxygen, and then you can eliminate out the halogen. Okay? So just a little idea of the mechanism.
I'm not confused as to like why that would happen at all.
Why it would happen?
Yeah, I mean, it's like you're picking up the metal to throw off the metal to make a less stable product with the charge.
No, so I mean something will take this. There may be some acetate here.
That's what you said, a minus is going to take that
A
H.
minus will take the H, and you end up with your neutral aldehyde. Of course, this can be further oxidized. Oh, you can go backwards. During test 3 and 4, we will reduce this to alcohols. I mean, you can go back and forth. But the carbonyl is a very strong bond. But we are putting in a pi bond. So you can say, is this thermodynamically favored? We're not doing any calculations. It may not be. But certainly a reaction that can take place. We're not crunching any numbers to really prove that. Okay. So here, What if you wanted to stop at the aldehyde? Primary alcohol to an aldehyde. Can you do it? We actually can. One of the important things is, if there's no water, then you can't do the further oxidation. If you want to stop at the aldehyde, the way it's done in lab is using a reagent called PCC. Pyridinium chlorochromate. This is the structure of it. Okay? Now there's variations of this. In the older textbooks, you used to have a reagent called PDC, pyridinium dichromate, or Collins reagent. I'm not even going to show you what Collins reagent is, but anytime you see any of these three, these are reagents that will stop at the aldehyde. And a big reason why is because these can be used without water. Where your big three, typically you have to have water. Because they're very ionic and they just won't dissolve if there's no water. This has more water solubility because you've got this carbon ring. And it turns out, in practice, this will work. So if you take this alcohol here, benzyl alcohol, one of the big three, what are you going to get? It's going to go all the way to the carboxylic acid. But if you take it with PCC and use a dry solvent such as dichloromethane, okay, and this sort of implies there's no water here, you can stop at the aldehyde. And you can get a good yield of your aldehyde. Now there's another reaction we need to show here. That is, how can you go from aldehyde to carboxylic acid? Collins. Well, guess what? The big three will do this. If you have an aldehyde and you treat it with sodium dichromate, it's going to do this. Just like if you had treated it with that. Okay? So there's another reagent that we can introduce. We'll see it later on. Collins reagent is a reagent that is only for oxidizing aldehydes to the carboxylic acid. And it involves silver ion. Ammonium hydroxide helps dissolve the silver ion. And of course there's water here. And the first step is forming the hydrate. And then the silver ion can oxidize the hydrate very similar to how this metal oxidizes that. But silver ion will not oxidize the alcohol. For some reason it will only oxidize the diol or the hydrate. It's a very unique reagent. But a lot of the importance here is it's actually another chemical test. Because when the aldehyde gets oxidized, the silver gets reduced. And it gets reduced to silver metal. Okay? Oxidation zeta +1 to 0. And the silver metal, if this reaction takes place, will be deposited in your flask, and it will look metallic. And if you're lucky, and usually it'll look like a mirror. You will look in there and be shining back at you. Okay? So a lot of times it's called a silver mirror. And so you could say, hey, did I get a reaction taking place? And the only functional group that gives the silver mirror is what? Aldehyde. So for example, if you think you have a carbonyl compound, and you narrowed it down to either an aldehyde or ketone, well, do a Collins test. Aldehydes will give a positive Collins. Ketone will not. Can you oxidize a ketone further? No. So it's a chemical test, it's a reagent, it's very specific to aldehyde. Of course, down here, how would you go from here to here? One of the big three. You can also use PCC. I think there's a page of problems in the workbook, for alcohol oxidation. Any questions about alcohol oxidation? Should be enough to get you for the lab. We'll see if there's any questions on Friday. Then we'll move on to oxidation of alkenes, which is in your handout. Please look ahead. Yes.